Okay. Today is 19th. Yeah, since you don't have any question, let me ask you a question, simple question. So, for and let me see how many of you could answer this. Uh, so, suppose Fn is a sequence of differentiable functions such that Fn converges pointwise. Functions on, let's say, on a set E converges pointwise on E if further assume Fn prime, this sequence converges uniformly. Does this imply that Fn converges uniformly? Hmm? So is it, the question is, suppose Fn is a different sequence of differentiable function and Fn converges pointwise. Assume the derivative sequence converges uniformly. Does that imply the original sequence converges uniformly? Yep. Is the question clear to everybody?
So I think no.
The question is not clear?
No, no, no. I mean, the question is clear. I mean, I think the answer is no.
Why?
So because you can always have a function such that the function itself isn't really bounded over the interval, but its derivative happens to be. So the function will end up converging only pointwise.
Hmm. Well, anybody have any other answer? Yeah. It does converges uniformly. Can you try to prove it? No, I'm not actually. I don't want your ideas. Just if you have any argument, please tell me.
So can we think of it like this? For
Yeah.
example, differentiability states from first principle. We know that f of x plus h minus f of x over h. This is equal to f dash x. So if f
Mhm.
dash converges uniformly, then for say for h1 and h2, we can for x1 and x2 we can write f dash x1 minus f dash x2. This the mod of this difference is less than epsilon when x1 minus x2 is less than delta.
What do you need to show? Fn converges to f. I mean, sorry. Fn converges uniformly means.
Okay, so basically I'm taking a function f which is its pointwise convergence, and then I just have to show that fn minus f is less than some epsilon whenever small n is greater than some capital N, where capital N only depends on epsilon.
Yeah, but that method, this method is not going to work.
Okay, so I was just thinking how we use the first principle of differentiability in this.
Oh no, you try to use some theorem of differentiability.
Oh, okay, sir.
Try to use some different. I mean, well, the limit function you don't know whether it is differentiable, right?
Yes.
There will be a limit function, but you don't know the limit whether the limit is differentiable or not. So you cannot use limit as such. Try to use other things. So without using, can you? What are the ways to without using the limit? What are the ways to show uniform convergence?
So can we think of it like this? So the uh, f dash of t will be uniformly Cauchy,
Okay,
right? So we need to show that f is also uniformly Cauchy to show that f converges.
true, right,
So I can add and subtract the f dash. Uh, so no. I can add and subtract the fn of t and fm of t to the
mm-hmm.
fn of to the function like fn of x minus fm of x. I can add and subtract fn of
Right,
t at a certain point inside,
okay,
and
right.
then use triangle inequality. So
That is true. You use triangle inequality, but
that
then
leaves me with that leaves me with fn of fn of x minus fn of t, and I
right,
think you can use mean value theorem here to show that it's less than
right. So the idea is to use mean value theorem. The idea is to use mean value theorem. You can use directly mean value theorem with on this fn minus fm and use triangle inequality. That is also possible. All right. So is this clear to everybody that you have to use mean value theorem here? Yeah. So you have to use mean value theorem. So you can actually right. So what you need to show? You need to show fn. I mean, you need to show Fn is uniformly Cauchy. That would be good enough to show that I mean, to Fn is uniformly convergent. Convergent. So now you need to actually, uh, I mean, use certain things. So you want to show Fnx minus Fmx. This one you want to show, but this one you have to use. So what, Sadbab, what did you tell? Fnx you want to add and subtract with?
A particular point, I think, if we use, then it will work. In the,
So you mean Fnt?
yeah, some t.
Okay. Plus Fmt minus Fmx, right? Then there is two extra term, right? It is not that easy, but you have two extra term. Plus Fnt minus Fmt, right? So t is fixed. T is any fixed point. So t in E is what? This is less or equal to Fn x minus Fmx minus Fmx, sorry, Fnt minus Fmt. This one plus Fm Fnt minus Fmt. See, Sadbab, do you see you cannot use on Fn or Fm
Oh, right. We have
mean
to use
value
on
theorem?
Fn minus Fm.
Right. You have to use mean value theorem on this Fn minus Fm. So this should be equal to Fn prime. This is x minus t times Fn prime, Fn prime sum x naught minus Fn prime x naught, right? This is for some x naught belongs to x and t, the interval joining x and t.
Sir, will x naught be the same for Fn prime and Fn prime?
That's a good question. So you are not using Fn prime and Fm prime differently. That is the problem, no? You are using
I
mean value
get it.
theorem on Fn minus Fm.
Oh, okay.
Okay, now you get the same
Right.
point. Yeah,
Exactly.
otherwise there will be problem. That problem would have been critical. The interval joining x and t. So this is, and then t is fixed. So fn converges pointwise. So this part is less than epsilon. So now since fn converges pointwise, since fn converges pointwise, so for every epsilon greater than 0, there exists n naught such that mod of fnt minus fmt less than epsilon for all n greater than n naught. All right, so this is 1. This is, put this as 1. This is 2. And right. So now, and also, since fn prime converges uniformly converges uniformly, so for every epsilon greater than 0, there exists n1 such that you choose this epsilon only. Fn prime x minus fm prime x is less than epsilon for all mn bigger than n1 and for all x in A. So this is 3. Now from 1 we get, excuse me, hello, अच्छा, hmm, hmm, yeah, sorry for this. Right, so from 1 we get mod of fn x minus fmx, fnx minus fmx is less or equal to b minus a, or whatever the interval, let's say e lies in interval a b. Of course, we need a bounded set. B minus A mod of Fn times epsilon plus epsilon, right? So mod of x minus t is strictly less than or less than equal to the interval. So that is the reason we get here interval. So E is subset of an interval. Now, so this hence for all x in E, for all n bigger than the max of n1 and n2, right? So this implies Fn converge, Fn is uniformly Gaussian. Is this fine with everybody? So any question here? So we actually, in terms of this is a fixed point, so we use point-wise convergent. And note that we don't need point-wise convergence at every point. Just at one point is good enough. So remark. We do not need point-wise convergence of Fn at every point. We just need point-wise convergence at one point only. Still, there is a gap here. Can you say what is it? Still, there is a little bit of gap here. Can you say what it is?
I think one of the n values depends on t.
Which one? No? Or this? Yeah,
Where
but
you
T is a fixed one. So you take the maximum, it doesn't matter. T is not there here.
But what if we take x arbitrarily far away from t? That b minus a
What?
term will be very large.
Which one? B minus A terms will be very large? No, this is ultimately a finite quantity. So this doesn't matter. So you can choose epsilon by B minus A if you want to get a epsilon. Epsilon
Oh,
by
you have
2
taken
times.
E as a subset of, okay, fine.
The problem is you need E to be interval to apply mean value theorem, right? So just arbitrary set will not work. So on this AB, we need an
Yeah, that
interval.
was what I was.
Yeah, so we need an interval. So if you look at a discrete set or disconnected set, you cannot apply mean value theorem in the whole, right? That is a problem. So you need an interval. So this was the problem. All right. Yeah. So is this clear? The proof clear? Yeah.
Yes, sir.
So answer is yes. Okay. Now let's come to the one of the main important theorem of this course. So
Hello, sir.
yes,
Sir, what if one of the endpoints of the interval is plus or minus infinity?
oh well, then it won't work. Then it won't work. So you need, so convergence will be uniform on compact sets, not hollow part,
Acha, okay, yeah.
right? So convergence, uniform convergence will be happening on compact set only, not hollow part or hollow the interval if you take one point infinity. Yeah, right. So Aditya was saying that this, yeah, infinity, same thing. So you need a bounded interval. That was the point. So you need a bounded interval to do that. Any other question? Any other question?
Sir,
Yes.
I just feel like can we drop this pointwise convergence part? I mean, if the derivative is uniformly convergence, can we? Is it possible to somehow show that the actual sequence will also be pointwise convergence? I mean,
No,
so
this is
can
not.
we
This
drop this?
may not be true.
Can you give me an example where the derivative sequence is? I mean,
Yeah, you
everything is.
can construct yourself. So can you tell me a sequence of functions which is very much increasing but derivative converges? Or let's say very big, but derivative is, let's say derivative is epsilon, but functional value is very big, greater than m. Can you give a function? Right. So derivative comes. So look at this linear kind of stuff. Linear functions. How does it work? So linear functions, it is of the form a plus bx, right? Now instead of a, the constant a, you put an n plus bx. Will it converges? Does it converge? Yeah, Saran, did you get it?
Yes, sir. Yes, sir. Got it. My mic was off. I was talking, but my mic was off. Yeah, I got it. Yes, sir.
Yeah. So remark one, maybe remark two, I should write it. Uh, one cannot drop pointwise convergence condition fully. For example, take a sequence fnx is n plus x, right? The derivative is fn prime x is 1 for all x. X is an interval I can take, no problem. So derivative fn prime converges uniformly on AB, but fn does not converge. All right, so is this clear to everybody? Yes or no? Is this clear?
Yes, sir.
Yes, sir.
All right. So next is a very important stuff, which is interchanging limit and derivative. What does it mean? So suppose Fn is a of functions, sequence of differentiable function on, let's say, open interval AB, but it's bounded. A, B, both less than mod A, mod B, less than infinity. Now you look at, so suppose Fn converges. The question is, maybe I should write not in this form, but Fn converges to F. Pointwise uniformly, let's write uniform. But your question can be asked pointwise convergence also. Now, is F differentiable? Yeah? So first question is this. Now second question, if F is differentiable, second question is, oh yeah, maybe it should be, if F is differentiable, is it true that limit Fn prime equal to F prime? So here you see you are taking derivative inside limit n tends to infinity, and here you are taking limit Fn n tends to infinity and derivative of it, right? So that is what we mean by interchanging limit and the derivative. Limit and the derivative. All right. So you have seen interchanging. So interchanging two limits you have seen. Two limits. This you have seen in terms of when we proved continuity. Right. So Fn limit n tends to infinity Fn t and limit t tends to x. Is it true? Limit n tends to infinity, limit t tends to x, Fn t. Is it true? So this one we have seen. We have seen this one. This is true provided Fn converges to, well, Fn converges uniformly. So we have seen a special case which we have seen that Fn is a sequence of continuous functions converges uniformly. So this star let me write. So if Fn is a sequence of continuous functions and Fn converges to F uniformly, then RHS of star is equal to limit n tends to infinity Fn x and LHS equal to limit t tends to x ft, right? Which is fx. This is what we proved, right? Uniform limit of continuous function is continuous, right? Follows from continuity of f, right? So we have seen interchange of limits. So even if Fn is not continuous, but Fn converges uniformly, you can prove this one. So this is an exercise for interested students. So that this Fn may be discontinuous, but if it converges uniformly, then this interchange of the limits is possible. Is it clear? Whatever I'm saying.
So that is just by definition, right?
What is by definition?
This the way you're like the what you're saying, because like on the right hand side is basically pointwise convergence. Okay,
No, this
on
is
a
true for all
discontinuous
x.
function. Okay, on a discontinuous function, right? Fn.
Fn may be discontinuous. So
Okay,
this is
okay,
not a definition. This is what we
okay.
proved. We have
Right, right, right,
proved
right.
that if Fn is a sequence of continuous functions and it converges uniformly, then we proved that f is continuous, and that is why the limit actually occurs. And this is nothing but fx. So this limit
Yeah, yeah, for
becomes equal
discontinuous.
for continuous function. Yes. But even if n is discontinuous, not continuous, but if n converges uniformly, then this limit interchange of the limits is possible. So those are interested, you can try to do this. Yeah. So now the question is this clear? Is this is the interest? This is a very interesting question. And so Fn is a sequence of continuous functions or differentiable function, and Fn converges to F uniformly. Is F differentiable? What do you think? Will it be differentiable?
Yes, sir. I think it is differentiable.
Yeah. Who said Shobik? Okay. Yeah. Somo was saying something.
So I think it will not necessarily be differentiable.
Okay. Not necessarily be differentiable. Do you have an example
Yeah,
right now?
if we consider the constant sequence of mod x, co- sequence of functions of mod x, then it
Uh-huh.
converges to mod x, and it is not differentiable, right?
No, Fn is not differentiable, right? So you're considering Fnx to be mod x also. So you need Fn to
Okay.
be differentiable. But your example is interesting.
Excuse me,
Yeah,
sir.
yes, Akash.
As Kanti said that we can take fx to be mod x, and we can take fnx to be the Fourier terms into expansion of mod x. Then the Fourier terms are
Fourier
differentiable,
terms,
but
does it converge uniformly? Fourier series, does it converge uniformly? Do you know even convergence of Fourier series?
oh no, we know about convergence, but it doesn't converge uniformly, right?
So I
Sir, if
said
it's
Yes,
Fn
sir.
uniform,
converges uniformly. Yeah, Fn converges uniformly.
sir, if it's uniform convergence, then the derivative will converge. I mean, then
Function
the
will be differentiable.
differentiable, yeah, because the because uniform convergence generally preserves all the properties of the functions fn, so it should preserve derivative as well.
Hmm. Yeah, anybody else? Well, actually, uniform convergence is good in the sense when you are considering continuous functions, but it's not good when you go to the differentiable. So this is here the answer is not differentiable. It just may not be differentiable. The example Sommo gave is actually works, but of course, as a limit function, not as a sequence function. So sequence we need to construct. So you consider fn
Hello,
x
sir.
to be square root of yes.
Sir, can we approximate the function mod x with the power series?
Mod x is not differentiable, you will not get power series. So for power
Oh,
series,
yeah,
you
yeah.
need
Okay.
differentiability. So this one, consider this one. Fn x is x square plus 1 over n, right? So is this differentiable function?
Yes, sir. It
This
is
is differentiable function. Where does it converges?
mod x.
Yeah, right. So check that. So check that. Fn x to be root over x square plus 1 over n is converges to fx uniformly, where fx, or rather I should not say like this. So I can for fn x, fn converges to f uniformly, where fx is mod x on, let's say, minus 1 to 1 open, not closed. Right, so you can check that, right? So this is an exercise. I'll leave it to exercise. And so here we get, so this example imply that uniform limit of differentiable functions may not be, is not necessarily differentiable, is not necessarily differentiable.
Sir,
Yes.
sir, when we first started pointwise convergence, we saw that
Yes.
pointwise convergence doesn't preserve continuity.
Right.
So we had to get some stronger notion of convergence.
Right.
Now that
Right.
convergence, uniform convergence doesn't preserve differentiability, can we have an even stronger notion of convergence that can preserve differentiability
Right.
as well?
Right. Yeah, we do have. We do have. We will not give the full notion, but yeah, I'll describe this one. But what you need that uniform convergence of the derivative as well. Not just uniform convergence of the uniform convergence of the function, you need uniform convergence of the derivatives to interchange these limits.
But then that will not work for the second derivative, may not work for the second derivative.
May not work for second derivative. So if you want to
So,
work for second derivative, you have to go to the second order
so can we have
uniform
something that
convergence.
can preserve all orders of derivatives?
Yeah, that is also possible if you have power series. If you have power series, then it is automatically possible.
Oh,
We'll
okay.
prove that. So once if it is power series, then it is infinitely time differentiable, and the limit of the derivative functions, the limit of the derivative partial sums actually converges and converges to the right one. So
Okay,
power
sir.
series actually convergence in the power series would give you whatever you want for every derivative. All right. So this is how you go stair by stair. So uniform convergence is very good in the category of continuity. Continuous functions, metric spaces. This their uniform convergence works very well, very very well. Now when you go to differentiability, it doesn't work. So you need to incorporate the derivative also. All right. You need to incorporate the derivative as well. So maybe let me state the theorem which we are going to prove next time, and we'll stop there. So theorem is, suppose Fn is a sequence of differentiable function on, let's say, open interval AB, where A, B both belongs to R. So we need a bounded interval such that one Fn converges pointwise Any question? Yeah, Tushar. Gayan Tushar Sanjay. So, what is your name? Which one? Gayan, Tushar, or Sanjay? Tushar, okay. So, Tushar, so you check it whether this is working. Good. So, it is good to have more examples. Yeah, X mod X, it will also work. It is once differentiable, but not twice. All right. So, and Fn prime converges uniformly to F. Then F is differentiable and f prime x is limit, yes, n tends to infinity e to power class fn prime x for all x in AP uniformly on AP. Yeah, is the statement clear? You need Fn converges pointwise. So pointwise, in view of this previous one, remark, pointwise convergence at one point is good enough. You don't need pointwise convergence everywhere. I wrote it to so that you remember this easily. Fn converges pointwise. Actually, Fn converges pointwise and Fn prime converges uniformly would imply Fn converges uniformly. So if you try to remember, you can remember Fn converges uniformly, Fn prime converges uniformly, then the limit will be differentiable and the derivative will be the limit of the derivatives. All right. So see, Fn converges pointwise and Fn prime converges uniformly would imply Fn converges uniformly. Right? Now, so it is easy to remember that the theorem is Fn converges uniformly and the derivative also converges uniformly, then the limit is differentiable. So uniform limit of differentiable function may not be differentiable, but if the derivative also converges uniformly, then it will be differentiable, and the derivative of the limit will be limit of the derivatives. Is this clear? Yeah, so we'll prove this next time. So if you have any question in 5 minutes, so I can answer those. And I'm thinking to be at least 5 more minutes. Uh, just as I mean, after class you might have questions which you may not be asking with all the people, so you can be there. I'll be five more extra minutes. If you have any question, you can be and ask. If other people go after other people goes, so just like after the class discussion after the class. Yeah, I'll share the notes. Oh, this week I've not shared. Yes, sure, I'll share it.